So we're now going to look at Newman projections, and we're going to look at how to draw them, the more stable and the least stable structures. So a Newman projection has two parts. It has a carbon atom that's shown in the front that looks like an upside down Y. So this would be the front carbon. It has an adjoining carbon that has a circle with 3 lines coming from it. And this would represent the back carbon. So we would put these two carbons together, the front carbon, and I'll draw the back carbon in red. So again, we would put these two carbons together where you can see the front carbon, that's in white, and the back carbon, that's in red. And what you're seeing here represents a Newman projection. So let's look at the following molecule, ethane, which is CH3, CH3. And we want to go ahead and draw out its Lewis structure. So this is the structure of ethane. And we want to label our carbons. This as carbon 1 and here as carbon 2. So we're going to look at carbon 1, and remember that is our front carbon. So here is carbon 1. So that's the upside down Y. And we want to go ahead and attach our hydrogen atoms. 1 at the top, 2 at the bottom. Then we want to draw our back carbon. Circle 3 lines. And again, this is going to represent our back carbon. And we want to go ahead and fill in our hydrogens. So what we want to do is put these two pieces together. We want to take the back carbon and we want to put the front carbon on top. And this represents our Newman projection. For ethane. Now the way that it is written, if we look from here to here, and we were to look at the angle, it is 180 degrees. So it is a 180 degree dihedral angle. The way that this Newman projection is written is called the staggered conformation, and it is the more stable conformation. Now we can rotate the front carbon. So let's again draw the back carbon. And what I want to do is take the front carbon and rotate it. And what you will notice is that the atoms are higher or closer together. They are higher in energy in terms of this structure. It is higher in energy. And this structure, if we look here, has torsional strain. And we're going to talk about torsional strain. We call this formation or this conformation eclipse, because the atoms are so close together that the dihedral angle is 0 degrees. Now the eclipse compared to the staggered is the least stable. So again, both of these structures are Newman projections. One is staggered and the other is eclipsed. So let's look at another example using more carbons. Let's look at butane. Butane has a formula CH3, CH2, CH2, CH3. And we want to draw the Lewis structure for butane. And when we draw the Newman projection, we want to view through carbon 2 and carbon 3. So we're going to number our carbons. This is carbon 1, carbon 2, carbon 3, carbon 4. So we want to view from carbon 2 to carbon 3. So let's go ahead and draw the front carbon. And this carbon here is going to be carbon number 2. So on carbon number 2, you have 2 hydrogens. So let's just go ahead and put them on the right at the bottom and on the left. And then you also have a methyl group. Remember, it's missing a hydrogen, so that's a methyl group. So we're going to put that on top. So that's our front carbon. So now we want to do our back carbon. So on carbon, and that back carbon represents carbon number 3. So on carbon number 3, you have 2 hydrogens. Let's go ahead and put those at the top, to the left, and to the right. And then we also have a methyl group. So let's go ahead and put that at the bottom. So let's put the two pieces together. We're going to start with our back carbon. And then on top, we want to put our front carbon. And if you take a look at how the structure is drawn, you should be able to see that this is a staggered conformation with a dihedral angle of 180 degrees. And remember, we said it was the most stable. You notice that we have actual substituents that are not hydrogens. So this conformation where you see the two methyl groups on opposite sides of each other is called anti. So this particular staggered is anti, and out of all of the staggered conformations, it is the most stable. So we are going to call this structure number 1. If I take that back carbon and I leave the back carbon how it is, and I take the front carbon and I rotate my front carbon, and you'll notice I have about 0 degrees here. So we're going to call this our second structure. And when I rotate, I go to the eclipsed conformation. And remember, we said eclipse compared to staggered is the least stable. Leaving that back carbon the same, and rotating that front carbon again. And if I take a look here, I have what is called steric strain, but I have a 60-degree dihedral angle. And if you look at how it's drawn, this conformation is also staggered, but with the 60 degrees, we call it a gauche conformation. And this is less stable than anti. Because remember, the anti-staggered is the most stable. I can, again, just to draw one more structure, and we'll call this one here structure 3. And the next structure I'm going to draw, we're going to call that structure 4. We leave that back carbon the same. And we rotate that front carbon. And again, what you see is a 0-degree angle. And this again is a confirmation that is eclipsed. So what you see in the staggered anti, again, the metals are far apart. They're on opposite sides. When you see the eclipsed, the atoms are closer together, a 0-degree angle. So we can essentially do what's called a conformational analysis, where we're looking at each structure, which is each conformation, and its rotation by 60 degrees. And we can look at the amount of energy per conformation to see which conformation is higher in energy, which conformation is lower in energy, which leads to stability. So when we draw the conformational analysis, we have the angles on the x-axis, and then we initially start our curves. In which we said the least stable would be higher in energy, and this would be structure 4. So the least stable is higher in energy. And that will correspond to our eclipse structure that's labeled number 4. Then we have here structure number 3, which is shown here. And that represents our least stable, slightly lower in energy, staggered gauche conformations. The very bottom which is our first structure, represents the most stable, anti-staggered conformation, and it is lower in energy. And then lastly, we have structure 2. And let's kind of modify our graph to kind of show that it's a little bit up compared to the staggered. And our structure 2 represents the eclipsed, that is labeled eclipse, that particular conformation. Lastly, we want to add, how can we go in between different conformations? And one that you may see often is being able to go from a Newman projection to a sawhorse structure. So we already know what a Newman projection looks like. So let's go ahead and draw an example. So drawing our Newman projection at staggered conformation. And let's go ahead and add some substituents. So I'm going to put Me for methyl. I'm going to use a bromine here. Again, I'm going to use Me for methyl. So here's our example of a Newman projection. Some things to keep in mind. If it appears on the right, you want the bond to be up and out, meaning that it's going to be a solid wedge. If it appears on the left, you want it to be in the page. And if it's in the page, that's the dash wedge. And lastly, if it's in the middle, if it appears in the middle, it's in the plane. So those are some guidelines. Also, when we talk about the dark wedge, which is your solid wedge, and the dash wedge, the position in the sawhorse, that's key, in the sawhorse doesn't matter. Again, the position in the sawhorse doesn't matter. So let's take a look at our structure. I'm going to draw the black line going down. And we said that if it's in the middle, it's going to be in a plane. So when we draw our sawhorse, we want to draw the plane. And this is going to represent our plane. That black line is going to be our guide. So in a plane, we know it's just a regular line. So that regular line is going to be here and here. We're also going to pretty much draw crosshairs where we have the bottom and we have the top. And then we know our right from our left. So at the bottom, we have a bromine, which is this atom here. And at the top, we have a methyl, which is this atom here. And we're drawing just a single line because that's our black line in the middle representing in the plane. Now we want to look above and below. So how we're looking at it, again, the red represents, okay, we want to come back here. I swapped these. My screen is swapped. So this is the left. And this is the right. So my hydrogen is on the left. It appears as a dash wedge. And my methyl is on the right. So it appears as a dark wedge. Now I'm going to look at the bottom. On the bottom, on the left, I have my fluorine. And on the bottom, on the right, I have my hydrogen atom. So this structure that we've drawn is the sawhorse. So all I did was just take my Newman projection, break it down into my left side, my right side, my top and my bottom and my middle, and using our basic guidelines that are shown here in white, I was able to draw a sawhorse starting with a Newman projection. And the way that this sawhorse is written, it is in the staggered conformation. If we viewed the Newman from a different direction, if we wanted to view the back carbon as being in the front, we would still follow these particular rules as well.